Last day we'd been looking at the fact that light travels in straight lines. We said that we couldn't really see how light travels because we only see it when light goes straight into your eyes. Here we can see a laser. We can see that it's shining and hitting my hand, but we can't see its path. However, if I spray some water on it, you should be able to see the path of light. The laser is reflecting off the water droplets and bouncing into our eyes, or into the camera in this case. We can clearly see the laser is travelling in one very thin ray, a straight line. So it's important to remember that light travels in straight lines. Also last week, I challenged you to build a pinhole camera. I don't know if you've done that, but if we have a little look back at some of the clips from the video that I gave you on how to do it, we'll have a look at some of the properties of the image of the pinhole camera. We looked at the filament of a bulb because we could see clearly what was the right way up and what was upside down. We had an image formed on the screen, and the image was dimmer, it was upside down, and the reason that happens is because light travels in straight lines. So now we're going to have a look at how a pinhole camera produces such an image. This is our basic setup. We had a light tight box, so a box that was sealed off. It had a translucent screen at the back, and there was one little pinhole that would allow light to travel into it. We also had a light source, which was a bulb. Now normally we can see a light bulb because the rays of light from the bulb travel in all different directions. It doesn't matter if you're standing above or below or behind the bulb, you should be able to see it because it's scattering light in every direction. Here I've got a number of rays of light showing some of the path that light might take. We're going to focus on just a single ray of light at a time. Now, that ray of light is not hitting the box. Let's assume it's now a ray of light in this direction, travelling from the top of the bulb. That ray of light is hitting the box. Can it hit the translucent screen? No, because it's hitting the opaque part of the box. There are other rays of light. They're a little closer to the pinhole, but again, they still cannot get into the box. It's only whenever you have a ray of light travelling from the bulb straight through the pinhole that that ray of light can keep on travelling and hit the translucent screen. Now there are rays of light travelling from all over the bulb that will do that, but we're just going to focus on a ray of light from the very top of the bulb at the moment. And we can see that it crosses over into the box and hits the screen, but it has to pass through the pinhole. If we look at a similar ray of light from the bottom that also passes through the pinhole, we can see those rays of light crossing over at the pinhole, which means a ray of light that started off at the top of the bulb is now at the bottom of the screen. And a ray that was at the bottom of the bulb is at the top of the screen. If we did this for every ray in the bulb that can pass through the pinhole, we would end up getting an image that is upside down. So it's that crossing over at the pinhole that makes our image upside down, like we saw in real life. Now you can also appreciate the fact that most of the rays of light don't go through the pinhole. Most are just hitting the box, which is why the image is so much dimmer. Most of the light doesn't get through to the screen. Only a very small proportion of the light leaving the bulb actually hits the screen, hence the dim image. But hopefully you can see there that the image is inverted. It's upside down. It's the same shape as the object, but it's fainter. Whenever we draw diagrams like this in school, instead of drawing a bulb to represent our luminous object, by tradition we use arrows instead. So here I've got an arrow, a blue arrow on the left hand side, and we can see a ray of light leaving the tip of the arrow, travelling through the pinhole onto the screen, and one from the base of the arrow, again travelling through the pinhole onto the screen. The image that's produced is the same shape as the original arrow. In this case it's a bit smaller, but it is inverted, it's upside down. We use an arrow because it's very easy to see, is it upside down or is it the right way up? You can draw this diagram into your notes. If we were doing this in school, we'd have to record our observations. What do you see on the screen? We saw the filament of the bulb. Move the camera closer to and further away from the light source. What happens to the image? Well, if you were able to do this at home, you'd be able to see, but as we move the camera closer to the object, the image also gets bigger. If you made another pinhole, you'd see a second image, the same as the first, appearing on the screen. And if we made one large pinhole, a bit bigger than a pinhole, we'd see the image get brighter, but also blurrier, because the rays of light travelling from the top of the bulb can hit the screen in a variety of places now, instead of the one small place as defined by the pinhole. So you'll have to draw this diagram again into your notes. And the important things to remember are that what we see in the screen is called an image. It is inverted, so it's upside down and back to front. And it's the same shape as the object. And it only happens because light travels in straight lines. This is important. This is evidence that light travels in straight lines. If light curved, the image wouldn't be the same shape as the object. It would be distorted. And there are a few notes for you to fill in as well. But I'll give you this page to copy. Another important phenomenon that we can see that only happens because light travels in straight lines are shadows. And you're all familiar with shadows. But not all shadows are the same. This shadow, you can clearly see is a shadow of my hand. Well, it's very dark. It's much darker than the surrounding wall. So we've got a very bright area and a dark area. And we can also see that it's a detailed shadow. It's a crisp edge to the shadow. It goes from light to dark, and you can see details like the shape of my hand precisely, even the hair in my hand. It's a single transition from bright wall to dark shadow. This shadow is different. You can clearly see it's my hand's shadow, but it's a much blurrier shadow. It's much less distinct. There's not this transition from bright to dark that's very sharp. There's a much more blurred transition. The shadow goes from dark in the center and fades away at the edges. We're going to have a look now at what the difference between these two shadows are and what causes them. The key factor that differentiates these two shadows is not the object. In this case, it was both my hand causing both the shadows. It's the type of light source. And there are two types of light source. We're going to call a point light source and an extended light source. What's the difference? A point source of light is a small source of light, where all the rays of light come from a single small point. This might be a bulb and a torch or something, but it's a single small source of light. Rays of light travel out in all directions from that source of light. Here we've got an opaque object, like a tennis ball or something, and a screen. Some rays of light don't hit the screen at all, they just pass away into different directions. Some do hit the screen, but in this case here, one ray of light that we've drawn hits the opaque object and is blocked. It cannot pass through an opaque object and so cannot reach the screen. We can use ray diagrams again to help us identify some of the properties of this shadow. So let's focus on a single ray of light at a time. This ray of light travels from the point source of light, hits the screen. No problem. On the screen, that point would be bright. As we lower this ray of light closer to the opaque object, it still passes by, still hits the screen. This ray of light just about passes the opaque object. So it does hit the screen, that area is bright. If we lowered that ray a little bit more, it would be blocked by the opaque object. It cannot reach the screen. So that ray, anything above that ray, is going to be bright on the screen. Areas below that ray are going to be dark. If we did the same thing on the bottom of the object, this ray of light just skims past the object. Anything below that second ray will be bright, anything above it will be dark. So eventually we'd end up with something like this, with a bright area above that ray, a bright area below the second ray, but in between those two rays it will be dark. We get this area of total shadow, and it goes from bright to dark very crisply. And that dark shadow is called an umbra. So an umbra is a shadow where no light has reached the screen. All the light from the light source has been blocked. And that's our dark shadow. That was like the first shadow we saw, the crisp, clear shadow. It goes from bright to dark very quickly. The second shadow was cast Because we had an extended source of light. An extended source of light is simply a bigger light source. That could be a window, it could be a fluorescent tube that you might have in school, those long light bulbs. It could even be a pearl light bulb. If you look at some light bulbs that you have at home, they're all white, and it's the whole bulb that appears to glow instead of just a little filament in the middle. Again, rays of light travel in all different directions out of this bulb, out of all parts of the light source as well. But again, we're just going to focus on a single ray of light at a time. So there's one ray of light that leaves the top of the light source and hits the screen. Again, if we lower it, it's still going to hit the screen. And lower it a bit more. That ray of light is the lowest ray of light from the top of the light source that can still hit the screen. A ray of light that went a bit lower than that will be blocked by the object. So that ray limits where the light hits. So above that ray, the light hits the screen, below it, it doesn't. Again, if we drew a ray of light from the top of the light source to the bottom of the object, very similar to how we had before, anywhere between those two rays, the light from the top of the light source would not reach the screen. However, this is a bigger light source. There are more places that light's coming from. If we drew two more rays, this time from the bottom of the light source, one skimming the bottom of the object, one skimming the top of the object, we get a slightly more complex pattern. And what we would see is something like this. Anything outside all of the rays remains bright. Anything between the two inner rays is entirely dark. No light from the light source reaches the screen. But in these two other areas, either side of the dark, we have partial shadow. It fades from dark to bright. And that's the blurred area around the shadow that we saw the first time. We still have an umbra, this dark area where no rays of light reach the screen. But we also have this blurred outside area called a penumbra. Rays of light from some parts of the light source can reach the screen, but not from all parts. In fact, the closer you get to the bright area, the more light hits the screen. So it's not the object that casts a blurrier or sharper shadow. It's entirely dependent on the size of the light source. A point light source has a crisp, dark, clear shadow called an umbra. An extended light source is larger and it will have a blurrier shadow with an umbra and a penumbra. In schools and shops, we often have very long light sources, and they can be so big, so extended, that essentially you lose any umbra whatsoever. Any shadow that appears is penumbra. The advantage of that is you don't get very dark shadows. So if you're writing something in school, you don't really want very dark shadows of your hand to fall on your page and get in the way of what you're seeing. So long light sources cause softer shadows. Again, let's have a look at your notes. So for a shadow to be formed, we need an opaque object and a light source. It has to be opaque to cause a dark shadow. However, translucent objects will also block a bit of light and therefore also cause some shadows. If you have a pair of glasses, you'll see that the lenses cast a bit of a shadow as well. But we're just going to focus on opaque objects. So a point source of light, all the rays of light come from a single point. This is what we saw a few minutes ago, and we got a dark shadow. The only reason this happens is because light travels in straight lines. Again, if light curved, it would curve around the object and fill in the area behind it. That doesn't happen. This is more evidence that light travels in straight lines. With an extended source of light, does the shadow still have a sharp edge? No, it's got a blurred edge. Is all the shadow equally dark? No, it fades from dark in the middle to light at the outside. Now, whenever you're drawing these diagrams, common mistakes are wherever the ray of light skims the object, it must skim the object. You must not have a gap between the ray of light and the object. It must not cross over somewhere else. What I'd like you to do for homework is this shadow size investigation. What equipment you'll need? You'll need some sort of light source. It could be a lamp, it could be a torch, any sort of light source that you have. You'll need a ruler or a tape measure, and you'll need a page to act as a screen, and you'll need another bit of paper that you can cut up, just a bit of scrap paper. And I want you to cut that into a little square of length 5 centimeters. Here it says ray box. You're just going to use your light source, be it a torch, it could be a light on a phone, if you've got the flash on your phone that you can turn on, it could be a bedside lamp. What you need to do is to hold your 5 centimeter bit of paper, your object, that's the bit that's going to cast the shadow. You're going to hold that 30 centimeters away from your light source. It might be useful to have somebody help you with this. You're then going to place the screen also 30 centimeters from the light source. So in this case, it's going to be right up against the object. And I want you to measure the width of the shadow. You might find it's easier to do that from the back of the screen, from the back of the page, as the shadow will be visible on both sides. And you're going to record the width of the shadow in this table. You're going to keep the object in the same place, and you're going to move the screen 10 centimeters further away. Record the width of the shadow. And keep repeating this up until you've got a meter between the light and the screen. It's important to remember that the object remains 30 centimeters from the light at all times. This last column, magnification, all I want you to do is to get the width of your shadow in centimeters and divide that by the width of the object. Don't forget the width of the object is always 5 centimeters. So you just keep dividing by 5. For conclusion, can you see what happens to the magnification as you increase the distance from the lamp to the screen? Just a simple sentence describing what you see.